talking about carbohydrates, and carbohydrates are actually compounds from the word carbo and hydrates. Hydrate means a compound that contains water in it. And actually, that's the formula for carbohydrate. It's actually water like this, and then you also put a carbon, and then you simply put N here and N here. So you are going to be changing the value for N. So N starts from 3 for this level. Like you can have 3 carbon carbohydrate, 4 carbon, 5 carbon, 6 carbon. At least you need to understand at this level 3 carbon carbohydrate, 5 carbon carbohydrate, and 6 carbon. These are 3. So this is the general symbol for carbohydrates. So you can see when you look at carbohydrates, the ratio of carbon to hydrogen to oxygen, carbon to hydrogen to oxygen is actually 1 to 2 to 1. You can see I've got 1 carbon, 2 hydrogens, 1 oxygen. Okay, please don't forget that. When we are classifying carbohydrates, before we can start talking about monosaccharides, you can classify them depending with how the carbon atoms, how the functional group is. Now, functional group, every time we're talking about organic compounds, we have got what we call a functional group. A functional group is a group that determines how the chemical properties and actually the physical properties for that compound. So specifically for carbohydrates, you are going to have a carbon double bonded to oxygen. Okay, this is the functional group for a carbohydrate. What do we call this functional group? This functional group, carbon double bonded to oxygen, is known as a carbonyl group. Carbonyl group. You need to differentiate it from a carboxylic or a carboxyl group. Carboxyl is carbon double bond with oxygen and then OH. This is known as a carboxyl. This one is found in carboxylic acids. But for carbohydrates, it's a carbonyl group. Now, for this carbonyl group that you can see here, depending with its location, it can carry a different name. Let's say I write a carbon atom, carbon here, carbon here, carbon here. So say we have got this same double bond with oxygen here. Now, each carbon atom, you need to know this, each carbon atom can only have 4 bonds. So the first carbon that I've written here, you can see it has got a bond down, and then I've written a double bond, so meaning that these are 3 bonds. So it has remained with 1 bond. So the other bond is going to be an hydrogen, because it is an, if it is an OH, that becomes a carboxyl. Okay, not carbonyl. And then this carbon on the middle, you can see it contains 2 bonds, so it needs 2 other bonds. So we're going to see an hydrogen and an OH. These are carbohydrates. They also contain OH groups. The carbon down contains only 1 bond, so it needs 3 more. So it's going to have 1 OH and then the rest are hydrogens. The carbon that contains a functional group is known as an anomeric carbon. Anomeric carbon. So this carbon here is known as the anomeric carbon. And you can see this carbon is bonded to how many things? Only 3 things. Okay. So a compound like this, when a carbon is bonded to, okay, let me not first talk about that statement. So we are saying when the functional group, like the carbon that contains the double bond, is at the end of a chain, that carbonyl group is now known as an aldehyde. So this is an aldehyde. And then you can have again, let me write something that is 3 carbon. So carbon, carbon, and carbon. But let's say the double bond with oxygen is here. So you can see this carbon already has got 4 bonds, so it can't have another bond. So this carbon on top has got 1 bond, so it can have 3 other bonds. 1 bond will be OH, and then hydrogen, and then hydrogen. and then also this one OH, and then hydrogen, and then hydrogen. So you can see the carbon, that the one that I've written here, the anomeric carbon is actually at carbon number 2. That's the anomeric carbon. Let me point at the carbon so that you will not think I'm talking about the oxygen. This is the anomeric carbon. It's carbon number 2. So if the carbon containing the functional group is on any other carbon other than the first carbon, not at the end of the chain, we call this as a ketone. This is a ketone. So both a ketone and an aldehyde, those we call them carbonyl groups. Why? Because it's a carbon with a double bond with oxygen. Another thing you have to know for monosaccharides, or basically carbohydrates, is that they contain not only the carbonyl functional group, they also contain the alcohol functional group. The alcohol functional group is OH. Okay, this is an alcohol or a hydroxyl. Yes, please. There's a question. Are we moving together, guys? You can't see the screen. Is there anyone that can see? You can now see? Okay, good. So make sure that you take note of this. So carbohydrates have got two main functional group. The carbonyl functional group is the main functional group, and the carbonyl can either be an aldehyde or a ketone. And then they can also have an alcohol functional group, which is OH. You can see each carbon should have an OH. If it doesn't have the C with double bond with oxygen. Hope this makes sense. Now, another thing that you need to know about a carbon atom is that when you have got a carbon atom that is bonded to four different things, okay, they should be different. Let's say you have got something like this, something like this. So a carbon that is attached to four different things, this one is known as a chiral carbon. Okay, chiral carbon. A chiral carbon is also known as an asymmetric carbon. So what is an asymmetric carbon? Please know what an asymmetric carbon is. This is a carbon bonded to four, and they should be different, okay, four different groups. If there are four groups but they maybe you had an H and another H, then it's not a chiral carbon. So the opposite is going to be true. If you have got a carbon that is bonded to less than four carbons, that is known as an achiral carbon. It's also known as a symmetric carbon. Or if you have got a carbon that has got four groups, but then any two of them are the same, you call that also as an achiral or asymmetric carbon. Does that make sense? Do we make sense, guys? Okay. Now let's talk about what is a monosaccharide, because this is the first thing we're talking about. Monosaccharide. So saccharide means sugar, and then mono means one. So monosaccharides, these are the simple sugar units. Simple sugar units. It is the simplest. You don't have two things which are bonding to give you the monosaccharide. It is the simplest that you can have. Now, monosaccharides, you can classify them looking at their number of carbon atoms. Another thing you need to know about monosaccharides is that these guys have got a general formula, which we already gave you. So the general formula for all monosaccharides is CnH2n or N. And this is actually the same as me saying C, okay, and then H2, and then O, and then I can now put N outside. It's the same, you can see, because N is common, I can factorize it. So this is the general formula for all monosaccharides. And we are saying that we can name monosaccharides depending with the number of carbons that they have. So you have got monosaccharides that have got three carbons. We call these as trioses. Tri means three. If you see the word os, that means sugar. So sugars with three carbons, because saccharide just means sugar. And then monosaccharides with four carbons, you can even guess the name. That would be a tetros. Monosaccharides with five carbons, who can guess the name? Those who did organic chemistry. That is going to be a pentose. And then anyone who can guess six carbons, what will be the name for the monosaccharide with six carbons? Even if you've forgotten organic chemistry, at least you should remember. So those are known as the hexose. Okay. You can also have those with seven carbons. Seven is hept, so we call them heptoses. But in this course, we are only interested in trioses, pentoses, and hexoses. Are we okay up to this end? Are we okay? Can I get a response? We are doubting. Are we fine? I want to make sure that people are good. Are we fine? Okay. So let's start with those monosaccharides that have got three carbons, which we are calling as the trioses. Remember from the general formula for the carbohydrates, therefore the trioses are going to have the formula C3, H6, or 3. Please differentiate. These are trioses. They are different. Let me even put it in another color so that you won't confuse it. Different from a compound that has got the formula C3, H8, O3. This compound is actually a lipid. Okay, this is a lipid. We'll discuss this one later on. So for carbohydrates, the way you are going to identify a compound to be a carbohydrate, whatsoever the formula they give you is, when you divide these three numbers, they should give you a ratio of 1 to 2 to 1. So if they give you C24, H48, or 24, this is also a carbohydrate, because you can divide it and it will give you a ratio of 1 to 2 to 1. If it doesn't give you that ratio, just know that that is not a carbohydrate. Now, the trioses of importance, you have got two. Okay, remember I said that carbohydrates can either be aldehydes or ketones, depending with where the carbon atom is. I mean the carbonyl group is. Another way in which we can represent these compounds is we can use lines. Okay, we can use lines. So we can have, this is carbon number one, this is a carbon on top there. Every point where we've got a line, there's a carbon. This is another carbon. And then we have got also this carbon. So let's start with this one. So for this molecule, we can have a carbon. So let's say the functional group is on the middle. So the double bond is on the middle. You can see where the double bond is. So because I've put a double bond on the middle, is this an aldehyde or a ketone? Anyone that can answer that? You people, are we following? So this is the, Now we have gone too far. Please ask when we are talking about the concept there, not when we have gone far, because it's a bit hard to go a lot of steps back. So if you see a carbon with a double bond on the middle of a chain, that is a ketone. If you see a carbon with a double bond at the end of a chain, that is an aldehyde. That's the only difference. Do you get that? I- i- If if the if the double bond with oxygen is on the middle, that's a ketone. If the double bond was oxygen was at the beginning, that is an aldehyde. Does that make sense? So when you look at this molecule that I've written like this, you can see there's a carbon with a double bond with oxygen. And then, so of the three oxygens, I've used one, so two are remaining. So one oxygen will go with hydrogen, another oxygen will go with hydrogen. So I've used up how many hydrogens? One, two. I've used up two hydrogens of the six, so four are remaining. Those four, one hydrogen will be here, one hydrogen is here, one hydrogen is here, one hydrogen is here. So those are there. Actually, here there's not going to be any hydrogen. Remember, we have got a double bond. Okay, so the other hydrogen will be here. We'll not have another hydrogen here because we said that each carbon can only have up to four bonds. So there is this bond one, there is this bond two, and then there is this bond three, there is this bond four. Okay, so that is why. So this is a trios. And the name of the trios, where so the way you count the carbons, you start counting from the end. So this is carbon number one here. This is carbon number two. This is carbon number three. The name of the trios where carbon number two is the one that contains the functional group is known as dihydro dihydroxyacetone. You need to know the name. It's not hard. Dihydroxyacetone. So this is our first trios. And dihydroxyacetone is what? A ketone. You can also have trioses which are not ketones. Instead, they are aldehydes. So I'm going to write also like this. But now, this is the same molecule, but it can appear in 2,2. So the double bond with oxygen can be at the end. You can see the double bond is at the end. Okay? And I said that, so you have got a carbon here. It has got a bond down, and then it has got two bonds with oxygen. So how many bonds are remaining for that carbon to be stable? Anyone to answer? How many bonds are remaining? It has got one bond down and then two bonds with oxygen. Yes, please. It is remaining with one bond. Very good. Because remember, a carbon can only have four bonds. So there is that hydrogen. So even here. Hope that makes sense. And then we can now put on the rest. We have already put a double bond there. So we are remaining with two carbons. Remember, this is C3. So this is carbon number one. Carbon number two is going to be here. Okay. That will be the next carbon. Let me use a different color there. Okay, we can have it here. So we're going to have OH and H. I've used up one OH. And then we're also going to have OH, and then the rest will be H's. Okay, so this is the molecule. Does this make sense? If you count the oxygens are three, the hydrogens are six, the carbons are three. Do we get the sense, guys? Do we get the sense? So just remember, this is a carbon here, right? A carbon there, there's a carbon here, and there's a carbon here. So three carbons. And then to each one of the carbons, just make sure that you put one OH and one OH. The rest of the bond should be hydrogens. That's all. Do you get that? So that's a, let's understand it here again. You can see we have got a carbon here, but the formula should be C3H6O3. So we are remaining with two other carbons. So another carbon, I'm going to put it here. Another carbon, I'll put it here. Is that okay? So we have got a carbon here, a carbon here, and a carbon there. Does that make sense, guys? And then what is going to happen is that I'm now going to change. You can see here the OHs were on the right. I'm now going to change. I'll put these OHs on the left. So we're going to have OH here and then OH here. And then the hydrogens are going to be this side. Do we get this? Oh, okay. So I've just changed. The OHs were on the right. I've now put them on the left. It's the same molecule. So this molecule, these two molecules, is actually the same compound. We call this as glyceraldehyde. Glyceraldehyde. Even this one is known as glyceraldehyde. Aldehyde. Now the glyceraldehyde where the OHs are on the right, we call it D-glyceraldehyde. The one that is where the OHs are on the left, think of left L. L-glyceraldehyde. Both of these are aldehydes. Why are they aldehydes? Because their functional group is at the beginning of the chain. They are both aldehydes. I'm doing this because I could have just shown you a picture of how these looks, but I want you to understand them because you should be able to identify them if they bring them in the test or exam. So how can you identify L-glyceraldehyde? You should be able to see the OHs. First thing first, you should make sure that you count the carbons should be 3. If the carbons are 3, it can either be dihydroxyacetone or glyceraldehyde. The next thing that you are now going to use is, okay, how do I know if it is glyceraldehyde or dihydroxyacetone? You look at the position where is the double bond with oxygen. If it is at the middle at carbon number 2, then it is dihydroxyacetone. If the double bond with oxygen is at the end of the chain, that is glyceraldehyde. If you have identified that it is glyceraldehyde, now ask yourself, is this D-glyceraldehyde or L-glyceraldehyde? You look at the position of the OH. Are they on the left or on the right? If they are on the left, that is L. On the right, that's D. Does that make sense, guys? Yes, please. Excellent. Mhm. Dihydroxyacetone. Dihydroxyacetone. All right. So, what are the functions of these trioses? You know, when these trioses, their function, they are used in cellular respiration. That's a function. Okay, a very easy function there. So I'll just put here function cellular respiration. You are going to understand, for some of you that you are going to be doing medicine, I'll be teaching you, and those of you will be doing pharmacy, biomed, cellular respiration. We will talk about these processes in biochemistry. So that is the function. Cellular respiration is the process by which we make energy from the food that we eat. So that's where these guys are going to come in. And then the next ones we need to understand are the ones we are calling as pentoses. How many carbons do the pentoses have? Excellent. 5 carbons. Therefore, their formula is going to be C5H10O5. Now, the function of the structure for these guys again, you can either have a keton or an aldehyde, just like we had for the trioses. Actually, that's what you need to know about all these. It can either be a keton or an aldehyde. But look at this, please. This one is a bit special. I'm going to write four of them. Okay. I'm going to write two in blue. I'm going to write two in green. Okay, I can use another color so that it's clear. Can put it in this one. So look at this, the way this is happening. If the functional group is at the end, let me start with the one where the functional group is at the end. So is this going to be an aldehyde or a keton? Anyone to answer? Is this an aldehyde or a keton? Very good. It's an aldehyde, isn't it? Excellent. Aldehyde. So what is going to happen for this is that I've already used up one oxygen, right? So that is carbon number one. Carbon number two will be here. I'll put OH there. Carbon number three will be here. I'll put OH. Okay. And then carbon number four will also be here. I'll put OH. So carbon number one, number two, number three, number four. For carbon number five, I'll also put OH here. The rest will be hydrogens. Hydrogen, 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 and hydrogen. It's actually this same molecule, but now I'll just change the direction of the OHs. Okay, just change the direction of the OHs, and then you are going to make a new molecule. Now look at this. You are looking at these carbons. Remember, this is carbon number one, carbon number two, number three, number four, and carbon number five. Actually, carbon number five, I can even write it like this because there is a carbon there, so I can write it like this carbon. And then can you see we have got these two hydrogens? I'll write H2. And then we have got this OH. I'll put OH. So the last carbon, instead of me writing everything the way I've written like this, I can simply remove them. Okay? I can remove them. And I'll simply put CH2OH. That's how we can write it also. Of importance, what I need you to know to remember here is that, so the same way I can also do for this molecule, I can just write the last one as CH2OH. Is there anyone who can see? It's breaking. Is it breaking for everyone? Okay, should be the network of our madam there. Either check some bundles or maybe just the network. Is it breaking for everyone? Okay, good. So you can see this molecule that I've written here. This molecule that I've written here, you can see where the OHs are, right? Like the direction of the OHs. They are all pointing on the other side. Okay. What I can do is that I can change the direction. I'll put the hydrogens this side. And then I'll put the OHs this side. So this molecule that I've written here is known as ribose. 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 So can you tell me which one is going to be L-ribose and which one is going to be D-ribose? Let's start with the first one. Is this going to be L or D? From what I told you, looking at where the OHs are, is going to be D. Very good, because they are on the right. And then this one also is going to be L, isn't it? Okay, so that is it. And then we can also write another. So these molecules are aldehydes. I can also have other aldehyde molecules like this. At the end, I can also already write CH2OH, CH2 OH. So I've already used up 2 carbons, so I can put 3 carbons on the middle, 3 carbons also here. Now I want you to notice this. I'm going to get, remember this is carbon 1, this is carbon 2, this is carbon 3, this is carbon 4. This is carbon 1, carbon 2, carbon 3, carbon 4. So if you just get ribose and then you go at carbon 4, where there is oxygen, you remove the oxygen, the name is going to change. Actually, not carbon 4, but carbon number 2. So if you get ribose, you go on carbon number 2, where there's oxygen, you just remove the oxygen. The name has changed from ribose to deoxyribose. Okay? But it's the same molecule. For example, if this is D-ribose, it has got hydrogen this side, hydrogen this side, and hydrogen this side. It has got OH here, OH here. Here, instead of me writing OH, I'll just put H. You can see it has changed from being ribose to deoxy. Deox means no oxygen. Deoxyribose. That is the same way with this one, which had H this side, H this side, H this side. It had OH this side, OH this side, and then here will change. Instead of, like I've gotten this one, which is here, instead of having OH, I've just have H. This is also deoxyribose. This deoxyribose is going to be known as deoxyribose because majority of the OHs are on the left. Actually, you look at the OH that is second from last. This one, the OH second from last, because it is on the right. Sorry, that's why it's D. Here it is on the left. This is L. Does this make sense, guys? Do we get the sense here? So these molecules that we can see here, the function is they are used in what we call nucleic acids. Synthesis of nucleic acid. This is going to be another topic. Specifically, ribose is used to make what we call RNA. That's we call it ribose. Ribonucleic acid. That's the RNA. And then for deoxyribose is also used to make nucleic acids. But the nucleic acids for this one is known as the DNA. Deoxyribonucleic acid. That's the meaning of DNA. Deoxyribonucleic acid. Hope that makes sense. Does that make sense? Does that make sense? Oh, too bad. Now the others are not responding, so I don't know if the network is here or there. Okay. So now all right. So let me talk about the last thing then for now. You can see this molecule has got 5 carbons. One, two, three, four, 5. And at carbon number 1, we have got a double bond with oxygen and a hydrogen. Let me use deoxyribonucleic acid, HH, and this is going to be OH. This is H. This is OH. This is H. And then the last one I said we can write it as CH2OH. So this is a molecule that contains 5 carbons, and this is the deoxyribose. So what happens is that for molecules that have got more than 3 carbons, they can form a ring for them to be stable. Please take note, if a compound has got 5 carbons, you get the second from last carbon, that is carbon number 4. If a compound has got 6 carbons, you get the second from last carbon, that will be carbon number 5. So you always get the second from last carbon. So what is going to be happening is this. The second from last carbon is going to go and react with the first carbon. Not only the first carbon, I want you to understand this. The second from last carbon is going to go and react with the carbon that contains the functional group, which we call the anomeric carbon. And what you are going to end up forming is going to be a ring. Now look at the ring that you are going to form. For this one, which is a pentose, we are going to form a ring that looks five-membered. So the ring is like this. So I'm going to write 2 so that you see the difference. So these are the rings that you'll be able to form. So if you start counting, this is going to be carbon number 1. This will be carbon number 2, carbon number 3, carbon number 4. Can you see carbon number 5 is the one that is down here? So carbon number 5 is actually going to be here, CH2OH. That is going to be the same way with this one. Carbon number 5 will be a CH2OH. Remember, this carbon is attached to this hydrogen and to this group. So that hydrogen is going to be down. That's the one that you can see here. Now for carbon number 1, what is going to happen is that the hydrogen that you can see here will actually react with the oxygen there to form OH. Okay. And then the oxygen that remains there is the oxygen that you are seeing at this point. But don't worry much about that. All I'm saying is that for carbon number 1, if you look at the molecule, can you see that carbon number 1 has got this hydrogen? So this hydrogen at carbon number 1 can either be on top or it can be down. That is what I want you to understand from there, because it's very important for you to look at that one. So it can either be on top or it can be down. And I've just told you that this hydrogen will react with this hydrogen, actually this OH can either go on top at carbon number 1 or down. So here it can either be down or it can be on top, the OH. And what this molecule is going to do is that when it forms, it will turn like this, it will turn in this direction. What's the importance of that? It means that the things that you can see this side will actually be down. So this is carbon number 2. So this is carbon number 2. Can you see that hydrogen is the one that is going to be down at carbon number 2? And then we have got this hydrogen, that one is going to be on top. And then at carbon number 3, this is carbon number 3. The OH is the one which is going to be down. And then the H is the one that will be on top. That will be the same way for this molecule. H and OH. H, H. If you look at these molecules and you quickly rush, when you count the number of carbons, you find that there are 5. You quickly rush and go and look at carbon number 2. If you look at carbon number 2, you have got hydrogen there. Just know that this is deoxyribose. If there was OH there, it means that that is a ribose. So for this molecule that I've drawn, look at this. The OH can either be down at carbon number 1 or it can be at on top. How do you know that this is carbon number 1? Between this carbon and this one. For carbon number 1, it is not bonded to CH2OH. So immediately you see the CH2OH, just know that that's not the carbon number 1. So the carbon number 1 is actually that one. This will be carbon number 2, this will be carbon number 3, carbon number 4, carbon number 5. So when you look at carbon number 1, if the OH is down, you call that as a beta molecule. So this is known as beta. Remember, this was coming from deoxyribose because the OH is on the right here. Please, you only form rings using the D molecule. The L molecule doesn't form rings. That is important. So this is known as beta deoxyribose. Now, a molecule that looks like this, like a pentagon, is known as a furanose. So we can also say this is beta deoxyribofuranose. If a molecule looks like an hexagon, like this one, you call that as a pyranose, but we'll discuss this in the next class. This one, which is here, because the OH is on top, this is known as an alpha. So this is going to be alpha D deoxyribose, also known as the alpha D deoxyribofuranose. So this is how you can be able to form the ring structures for these compounds.